Hi everybody, and welcome to our screencast of Giancoli's Chapter 15, Laws of Thermodynamics, where we take all the pieces that we've been working on and put them together to study real complicated systems like car engines and whatnot. As you go through the chapter, I'm expecting that you're going to outline some things. These are some terms you will certainly come in contact with, and what we're going to do in this guide is work through these step by step and also give you the skills that you need to be able to handle problems of even the most complicated sort. So away we go. In that first lab experiment of the year, you did a proof where you showed that force times distance, which you know is equal to work, turned out to be exactly the same thing as pressure times a change in volume. And it makes all the sense in the world. The way we did the experiment was we had a little syringe, and originally our syringe took up a whole container full of gas. And what we did is we pushed down on that syringe until maybe the gas was only allowed to occupy half of that distance. And we had a force, we had a distance, and we also had pressure times change in volume. Now, in the next slide, what we want to do is take a look at what that looked like on a graph. When you graph the data for this experiment, you got this kind of graph right here. And if we were to do that lab again and we were able to look at the graph happening in real time, what you'd see was something like this. The syringe starts out with plenty of gas in it, taking up plenty of volume, but that gas is at low pressure. So that's this state right here. And if we slid up the graph, what we've done is now actually done the lab. We've squeezed the gas, and so now it doesn't take up a whole lot of space, but it's at high pressure. So, furthermore, let's finish that thought. If we let the syringe come back to its original place, we would end up right back where we started. So no change in volume equals no work done. So what we're going to do right now is throw one really important idea out there that you want to keep in mind, and that is that if you have area under your graph, meaning if you actually etch out a closed shape on one of these pressure volume graphs, then you can get work done. And what we're going to do is take a look at a series of situations that'll add up to that kind of arrangement. Okay, so here we go. In this slide, what I'm going to do is give you the general rules of the road and show you one example that's kind of typical about how work gets done by a gas. The way it works is that if you move around a pressure volume graph like so, let's say you start with the gas in some, they call it a state, right there. So it's some pressure and some volume. What will happen is we let the gas slide down here, just like our syringe did. So we're going to say that's state number 2. Some transition is going to happen where maybe we do that, and what will happen there is we'll create another state, state 3. We do something like that, end up in another state, and finally close the loop. And the whole idea is that what I've done now is I've created area. I've created area under the pressure volume graph between my states 1, 2, 3, and 4, and that's how you get work done. Now the basic rule of thumb is like this. If you notice, the way I did this series of transitions was I worked them clockwise. So clockwise means you get work out of the gas, and that's usually the way we like to do it because we're trying to get work done to power our cars or whatnot. But if you can do it the other way too, there's some situations where you run a pressure volume graph counterclockwise, and that would be corresponding to work in. So what I want to do is work through a series of small examples that show you how all these different pieces can fit together and show you what's going on with each one of them. No matter how simple or complicated the problem is, there are 3 variables, pressure, volume, and temperature, that describe what they call the state of that gas. And what we're going to do as we look through different examples is pay attention to what's going on with pressure and volume. Now pressure and volume you're going to see because they're on the graph, but you really want to think as you go through these, what's happening with temperature? What must temperature be doing to account for what I'm seeing? So in an isobaric transition, what's going on is we'll start at a gas in one state, let's say out here, and let's make that gas move to some kind of state over here. So we've got state 1, state 2, and we'll make up a couple numbers to go along with this. Let's just say that volume number 1 is 3 cubic meters, and volume number 2 is 1 cubic meter. And let's say that that whole thing was done isobarically, so at a constant pressure of, let's just say 100 kilopascals. Notice all the metric units. So if I were to go ahead and ask myself, is there work being done? There's a couple of ways to answer that, and they both say yes. the way we've always done is to say, well, is there pressure times the change in volume? And you'll say, yeah, there definitely is. There's 100 kPa's. There's a change in volume of 2 cubic meters. And is there work being done? Yeah, there's no doubt about it. This is going to be 200,000 joules worth of work that was done. The other thing you want to notice, though, is what was going on with the area under the curve. There is area under the curve, and that's how you can say again that there was work being done. The last thing you want to think about is why would this take place? If you notice, we slid the gas from volume to volume, we kept the pressure constant. Now what were we doing with the volume? We were squeezing it. So how could that possibly happen? To squeeze a gas but still keep the pressure the same? There's only one way. If the graph is going the way we did it, we changed the temperature. We actually dropped the temperature to keep the gas exerting a constant pressure as we squeezed it from state 1 to state 2. So just bear that kind of thing in mind. You just want to keep it in the back of your head because it's important what's going on with the temperature. Okay, so that's isobaric. The next type of transition we can look at to pick up on where we left off might be this. If we have a gas that's at 1 cubic meter, and let's say that's its state right there, and 100 kilopascals, if we were to do a transition like this, where we slide the gas from one pressure to another pressure, let's say 200 kilopascals, then what we're doing is called isovolumetric. And that's pretty obvious because what we're doing is keeping the volume constant. So is there any work being done in this situation? Well, think about it. Work equals pressure times change in volume, right? So it looks like in this situation there is no change in volume. All there is change in pressure. But is there a change in temperature? Think about that. What we're doing is we're not squeezing the gas, keeping the gas a constant volume, and yet pressure is going from 100 to 200 kPa's. Sounds to me like we're heating the gas. Sounds to me like we're maybe dumping energy into it. The temperature's going up, so the pressure's going up, but somehow we're managing to keep the volume constant. Actually, when you think about it, you know what that sounds like? It sounds like an isovolumetric situation is a lot like a bomb. Yeah, right. Okay, moving on. The third type of graph we're going to look at is called isothermal, and it's one you've actually got a lot of experience with. When we did the Boyle's Law lab, you might remember that temperature was actually being held constant in the course of doing that. And the way that that might work would be if you would squeeze the gas and you were going to force it to go up the graph like so. You were going to do it in a way that was going to be slow enough so that any work you might dump into the gas would have a chance to eke away and heat could bleed off to the classroom, and then you'd never do anything except keep the temperature constant. Now, what I want you to think about is a situation here where you've got the gas in a state. It's got a certain pressure and a certain volume, but it's also got a certain temperature. Remember, you can't see the temperature, but it's there. What I want you to think about is that if you had the same gas, but it was cooler in the room, so say we'd cooled the classroom down by, maybe 100 degrees Celsius, then the gas might look like this. Same volume. The gas is still going to fill that same syringe, but what's going to happen is it's going to exert a lower pressure at that volume. And what you'd end up with if you graphed that kind of situation is another kind of inverse curve, like so. Now, both of these things have a special name. They're called isothermals or isotherms. And the deal with isothermal, again, is that you hold temperature equal to a constant. So what we're going to do is look at this couple of isotherms that we've set up and simulate a real-life kind of transition. We've got a gas in state number 1, so it's got some pressure, volume, and temperature. And what we're going to do is we're going to push it up to state number 2. So how did we do that? Well, let's think about it. We did a volume change where the volume's getting smaller and the pressure's going up. That means we're squeezing the gas. So what are we doing? We're putting work into the gas. So a transition that goes this way has us doing the work. And there we are at state number 2. So the next transition we're going to do is to drop right on down there, and this is an isovolumetric kind of step. So in isovolumetric there's no work that's being done, but let's think about it. Why would a gas go from state number 2 to state number 3, drop the pressure while keeping the volume constant? It's being chilled. So what's happening is the energy is seeping out of the gas and it's dropping down to a lower temperature. Now this next part is where you really want to pay attention. What we've got is a transition from state number 3 on down to where we're almost done in state number 4. And what's going to happen now is the gas is going to expand. So just like it did when we let our hand off the piston, this gas is going to expand and it's going to do work for us. Here's the deal. Watch this. We're going to grab a new color, and if I were to go ahead and color in the work that was done in the first part of this graph, it would look like this. I would shade in everything like so. So red means work that we've done. Now, what's going to happen is ultimately we're going to get some work back out of that gas, and that's what happened for us in step number 3 to 4. And this is the kind of energy that we would get back. So if you look at it, there you go again. It's what we said in the first place. When you go counterclockwise around a PV graph, we're doing more work here on the gas to get it from state 1 to 2 than the gas is doing back for us as it goes from state 3 to state 4. And that difference is going to be the amount of work that we end up putting into the gas. And since we'll go really high tech, let's see how this works. It looks like in the middle, no, it's not high tech. It was supposed to be multicolored, but it wasn't. So in the area in the middle is going to be the amount of work net that we put into the gas in this case. And then we finish the whole thing off by going and doing a transition from 4 back to 1. And what's that going to mean is we dump some more energy in the form of heat into the gas and crank the temperature back up at a constant volume. And we'll get back to number 1 and we could repeat the thing. So there you go. That's a heavy-duty transition, and that's what it looks like. The fourth and final kind of transition we're going to talk about is one called adiabatic. In doing all these different transitions, we've talked about the state of the variable, the pressure, the volume, the temperature. And as I've been saying, you want to really keep in mind what's going on with all those as you work through these transitions. So this is a good example because it's got a lot of things going on with it all at the same time. We gave the example in class earlier of a thing called the Chinook wind that happens in Canada. And here's an example. Here's a graph of how that would actually operate. If we've got an air mass that's hanging around at the top of a mountain, it's got a certain volume right here, and it's operating at a pretty low pressure. What happens is if that air mass drops down quickly to lower altitude, that means the pressure on it will crank up. And the key is, if it does it quickly, what will happen is we'll get a state where, because the transition is so quick, the amount of heat, Q, that can enter or leave the gas, in this case, is equal to 0. And what goes on, if you think about it, is that if we have gas that's being squished, somehow, that's what's going on here in this transition, then the only thing that can happen is if work's being done on the gas by gravity, there's only one place left for that energy to go, and that's into the internal energy of the gas. Because no heat can bleed away, what happens is you get those crazy temperature increases where you have something like 70 degrees increase in temperature at a time. Now the thing that's good about an adiabatic transition from your point of view as a problem solver is that, in a way, it's so complicated. There's pressure, there's volume, there's temperature all happening at the same time. And because it's complicated, what people that write textbooks do is they make it so that you don't have to really stress over those things, and what you'll be able to use is information that they give you, as long as you know that the heat that's entering the system or leaving the system in an adiabatic transition is 0. And so any work that gets done by the system or on the system comes out of the internal energy if the system's doing work, or it goes out of the internal energy if the system's doing work for you. And there you go, that's adiabatic. So what we'll do is just sum up all those things up, and then we'll get into some doing